Jai Hind. The topic for today's lecture is concurrency control. It comes under the category, it comes under Unit 5. So basically, we are aware in the previous unit, we have seen what is the meaning of concurrent transactions. So once we are having a concurrent transaction in the system, so we need certain mechanisms to maintain, to control their concurrency. And this is being done by the concurrency control manager, a component of your DBMS. So concurrency control is the management of concurrent transaction execution. DBMS implement concurrency control techniques to ensure serializability and isolation of transaction in order to guard the consistency and integrity of the database. So in serializability, we ensure the isolation, and in the concurrency control, we ensure that consistency and integrity of the database remain same. So concurrency control can be performed by DBMS with various methods. And what are these methods? We will going to discuss one by one. We are having locking methods, time stamping methods, and another category is the optimistic methods. Log-based methods. So most commonly used technique to control the concurrency is based on the concept of locking the data item. So locking the data item, suppose I'm having two transactions, T1 and T2. T1 also wants to work on Q, T2 also wants to work on Q. Then in that case, what will happen? T1 will lock this data item. It will perform its action on this data item, and once its work on the data item got completed, only after that T2 got the permission to work on data item Q. So this is locking protocol. So a lock on a data item, it specifies the status of the item with respect to possible operations like read and write that can be applied to it. So if a transaction T wants to modify a data item, so a lock must be associated with that data. It must lock that item. If any other transaction T2, for example, already access the same item, then T1 has to wait until T2 gives up the lock. Otherwise, T1 locks the data item and proceed. Now we are having two kinds of locks in database. One is my exclusive lock and another is my shared lock. What's the exclusive lock? It is represented by the symbol X, and shared, it is represented by S. So we are having X mode and S mode. What is X mode? That is exclusive mode. The data item can be both read as well as written. X lock is requested using lock X instruction. That is, if I am having exclusive mode, then T1 can read as well as write on this data item Q. But if T1 has obtained the lock in the mode S, then in that case only reading is allowed, writing is not allowed. So we are having two, X and S. In the case of the exclusive, read as well as write, both rights are given to the transaction. If this particular category is being used, then in that case, the transaction has the permission only for the reading and not for the writing. So lock requests are made to concurrency control manager. The concurrency control manager will check if the lock can be granted or not. If it can be granted, then it will give the lock to the transaction. Otherwise, the transaction has to wait. So how once we are having two types of modes of locks, we are having a lock compatibility matrix. Why we need a lock compatibility matrix? For example, T1 has obtained the lock on Q on S mode. Then in that case, it can read. Now T2 comes, it also wants to read. Then it should, because earlier in the conflict serializability, we have seen that read and read operations, they are my non-conflicting instructions. Then in that case, the T2 should also be allowed to go for the reading part. But if it wants to go for the writing part, then it would be denied. So how my concurrency control manager will check that which are the compatible modes and which are non-compatible modes? For this, it uses the lock compatibility matrix. Here, if then we are having true, otherwise if we are having S, we wants to go for X, then lock won't be given. Similarly, XS or XS, then the lock will not be given to the transaction which is coming later on. So a transaction may be granted a lock on an item if the requested lock is compatible with locks already held on the item by other transaction. Any number of transactions can hold shared locks on an item, but if any transaction holds an exclusive, then no other transaction may hold any other kind of lock on the item. So if a lock cannot be granted, the requesting transaction is made to wait till all the incompatible locks held by other transactions have been released. The lock is then granted. This is an example of a transaction performing the locking. So since the reading is required, locking and then unlocking, reading, locking, unlocking, and then we are displaying. This is how we will do the things. So locking as above is not sufficient to guarantee the serializability. If A and B get updated in between the read of A and B, the display sum would be wrong. For example, what will happen? After that, this is my T2. Okay, my T3 started execution after this point. Okay, now exclusive, it can be given. After that, that is, once the T2 unlock A, the processor, it starts executing the next instruction T3, transaction T3. Here, this set of operations got performed. We updated the data item A. Once, then again, my processor, it shifts here, after this particular set of instructions got executed. And then when we display A plus B, what will happen? Now in this case, A has been updated, but it is still working on old A value, and my results, they are wrong. So serializability, if we say that we are doing the locking and my serializability would follow, that is, my consistency remains, would not get affected, then the answer is no. A locking protocol is a set of rules followed by all transactions while requesting and releasing the locks. So consider this particular schedule, neither T3 nor T4 can make progress. What is happening in this case? It has exclusive mode, now A, and it wants the shared mode in B, but it is not been unlocked here, and it wants exclusive X on A. Then this is an example of the deadlock. So here we are having a deadlock condition. So to handle a deadlock, one of T3 or T4 must be rolled back and its locks are released. How we handle the deadlock, we will see in later on lectures. So how we will guarantee the serializability? We will use this locking mechanism in certain way, in a certain order. So the very first algorithm is my two-phase locking protocol. What it says, to avoid the starvation of transactions by granting the locks, we use two-phase locking protocol. So here I am having two phases. One is growing phase and another one is my shrinking phase. In growing phase, what is happening? The transactions, they may obtain the locks, but the transaction may not release the locks. In phase 2, that is once the shrinking phase starts, in this we start releasing the lock, but once we have started releasing the locks, then the transactions, they cannot go for obtaining the locks. That is, they cannot make request further for locking an data item. Now two-phase locking protocol, they follow the conflict, they ensures conflict serializable schedules, but they cannot prevent the deadlocks. And in case if you want to prevent the deadlock, they cannot prevent the deadlock. So cascading rollback is possible under two-phase locking protocol, because we have seen earlier in this example that it is a mild deadlock situation, and the simplest solution to once the deadlock is detected, the simplest solution is to roll back the transaction. But if you are rolling back the transaction, then there may be the possibility we need to go for the cascading rollback. That is, what is cascading rollback? In the case of the cascading rollback, if we are rolling back one of the transaction, then we need to roll back other transactions due to the conditions that is they are working on certain data item, and due to this shared data item, and due to this the other transactions, they also need to be rolled back. To avoid this, follow a modified protocol where which is called the strict two-phase locking. Here transaction must hold all its exclusive lock until it commits or aborts. That is, once you start unlocking, you should go for the commit operation. How we implement the lock? A lock manager can be implemented as a separate process to which transactions send the request for locking and unlocking. The lock manager replies to a lock request by sending a lock grant message or a message asking the transaction to roll back if there is a deadlock. The requesting transaction wait until its request is answered. The lock manager maintains a data structure which is called the lock table to record the granted locks and all the pending requests. The lock table is usually implemented as an in-memory hash table. We use the data structure hash tables, which is indexed on the name of the data item being locked. So here, this is the you could say my hash table, lock table, which is implemented with the help of hash table. So here the black rectangles, they indicated the granted locks, white ones, they indicated the waiting request. So here I am having I7, I23, these are my you could say my data items. Here T2, this is my transaction, it has been granted on the lock on this particular data item. And these are the two transactions who have got the lock on this, but this transaction is waiting. And if you look at the figure, we have followed a mechanism, a linked list mechanism. So in this case, the pending requests, they are always at the end. So lock tables also record the type of lock, granted or requested. New request is added as the end of the queue of request for the data item and granted if it is compatible with the earlier locks. That is, in this case, it is going to be SS. Unlock request result in the request being deleted. That is, for example, it sent the request for unlocking. So here it got deleted from the list. And later requests are checked to see if they can now be granted. If transaction aborts, all waiting or granted requests of the transaction, they are deleted. The lock manager may keep a list of the lock held by each transaction to implement this efficiently. Another set of protocol, it is my graph-based protocol. In the case of the graph-based protocol, they are alternative to 2PL. We impose a partial ordering on the set of the data item. These are my data item, and we implement on data which need to be executed first, and then D2, and then D3, and so on. So if we are having an H from DI to DJ, then any transaction accessing both DI and DJ must access the DI before using DJ. It implied that the data that the set D may now be viewed as a directed acyclic graph called a database graph. The tree protocol is a simple kind of graph protocol which you can use. So here only exclusive locks are allowed in this case. So here if this particular H, then you can go for J. So the first lock by TI may be on any data item Subsequently, a data queue can be locked by TI only if the parent of queue is currently locked by TI. This I already told you that if I am working on this, then I can unlock, I can lock on data item J. If I want to lock this data item D, then I am not allowed to do so. So data items may be unlocked at any time. A data item that has been locked and unlocked by TI cannot be relocked by transaction TI. So the tree protocol, it ensures the conflict serializability as well as freedom from deadlock. Unlocking may occur earlier in the tree locking protocol than in the 2PL. In the case of the 2PL, we are unlocking once the shrinking phase starts. Whereas in the case of the graph protocol, there is no such restriction. So what is happening? We can unlock the data item earlier also. So a shorter waiting times and it increases the concurrency. Protocol is deadlock free, therefore no rollbacks are required. So these are the advantages of graph-based protocol over 2PL. But yes, it contains certain drawbacks. Protocol does not guarantee recoverability or cascade freedom. So we need to introduce commit dependencies to ensure the recoverability. That is something happen, then the schedules, they are not recoverable. Another drawback, transactions may have to lock the data items which they are not using. So it increases the locking overhead, and due to this locking overhead, there is additional waiting time. So another problem is it will go for the decrease in concurrency. Another set, that is my third category, that is timestamp based protocol. In the case of the timestamp is assigned by the database system before the transaction TI start the execution. If a transaction TI has been assigned the timestamp TS and a new transaction TJ enters, then the timestamp TI is always less than the timestamp of TJ. And how we implement it? Either use the system clock or use the logical counter concept. That is logical, that is I. Once TI comes, assign I value to TI, increment I. Once the TJ comes, then allocate your incremented I value, that is I plus 1, to the TJ as a timestamp value. So each transaction is issued a timestamp when it enters, and how we find that which transaction is coming first and which coming next with the help of this concept. The protocol manages concurrent execution such that the timestamps determine the serializability order. In order to ensure serializability, the protocol maintains for each data item two timestamp value, W timestamp and read timestamp. W timestamp is the largest timestamp of any transaction that has executed write queue successfully. Similarly, in read is the largest timestamp of any transaction that executed read queue successfully. What is timestamp value? That is this value. So, what is the protocol? The timestamp ordering protocol ensures that any conflicting read and write operations, they are executed in timestamp order. And how it does? Suppose a transaction TI issues a read queue, then my system will check the things. What it will check for the read queue? If TS of TI, that is which is going for the read operation, if the timestamp of this transaction is less than or equal to the W timestamp of this data item, then this implies the TI needs to read a value of queue that was already overwritten. Hence, the read operation is rejected. Because what we are saying, W timestamp, it is the largest timestamp of any transaction that executed the write queue successfully. Then in that case, what is happening? This value has been overwritten and my TI is trying to read some overwritten value. So this read operation need to be rejected and TI is rollback. If the timestamp of TI is greater than or equal to read timestamp of Q, then the read operation is executed. And once it is successfully executed, what will happen? You need to update R timestamp and it is set to maximum. That is the what is earlier value, the earlier value of read timestamp and the TS value of TI. Whichever value is maximum, you assign that value to this. This need to be done once you are reading, once a transaction is reading on the data item Q. If a transaction TI wants to write, then it need to check again. There is a checking. What it check? It check if the timestamp of TI is less than read timestamp of Q. Why? Here, look. Once you are going for the reading, then you are checking with W. Why? Because read write is my conflicting. You are checking for the conflicting. You need to maintain the order for the conflicting instruction. In the case of the R and R, what is happening? No confliction is there. Okay. So, here I am having a write. Now, W conflicting comes with write and conflicting comes with the write instruction. So, you need to check with both R as well as W timestamp value. So, first we are checking with the R timestamp value. If the TS value is less than R timestamp, then the value of Q that TI is producing was needed previously. Okay, and now it is not further required. So, here write operation is rejected and TI is rollback. Now, check for the W. If the timestamp is less than W timestamp of Q, then TI is attempting to write an obsolete value of Q. Again, it is trying to write an obsolete value. Then again, in this case, write operation is rejected and TI is rollback. Otherwise, the write operation is executed and W timestamp is set to timestamp of TI. No need to go for max function as we have seen in the case of read operation. So, here it is a partial schedule for the data for transactions T1, T2, T3, T4 and T5. And if you look here, what is happening here? My timestamp based protocol, it is working. This is again the same case. So, this is all about, so we have seen 3 protocols today under this in today's lecture. The first protocol is my locking based protocol. Then we have seen the tree protocols, and the last one we have seen the timestamp ordering protocol. We are having other sets of protocol also for the concurrency control management, which we are going to discuss in next lectures. Thank you and Jai.